Science, WC University Science Series, Stepping Stones in the Development of Modern Physical Thought. So today we are on lecture number 3, From Backwoods America to the Courts of Europe, Benjamin Franklin, Sir Benjamin Thompson, and the Beginnings of Classical Physics. So we have one more lecture that's happening this fall, and that's going to be on the 21st of November here in the Commons. It's a Tuesday, 2 o'clock. And then we have 5 lectures that are planned for the spring. So Julius is going to take a look at some dates that I gave him today, and once those are confirmed, I will get those out on the website, because I understand that you guys want that information as soon as possible to put on your calendars. So I will try to get that out. And if you do not use the website, but you want that information, just let me know, and I will type it up and put it in your box. One other little note, we do have the French Club meeting today at 3 o'clock behind us, so I just ask that when the lecture is over, if everyone will leave by the front door rather than the back door so we don't disturb them. All right, and I think that's all. Julius?
All right.
Thank you.
Thank you, Susan. Am I live? All right. Is this thing's working? Okay. Well, I appreciate everybody coming out on such a lovely spring day. Spend a little bit of time here. Just to sort of set the stage, the last 2 lectures we were talking about the time period of the 17th century and before. And this one is very much an 18th century talk. Newton had written his Principia, Voltaire had popularized it, and the notion that physical laws dominated the universe, understandable physical laws, had come to fruition in the 18th century. The notion of what was called a clockwork universe. The creator had created this thing and wound it up, and it was winding down now according to these immutable laws. So today we're going to be talking about 18th century physics. And I should say that these two characterize that age as much as anybody else in quite different ways. Curiously, as I was thinking about this, I was thinking about the term that I learned in first year French for this century called Le siècle de lumière, the century of lights. I guarantee you, if you Google the century of lights, you will not find anything historical. You will find all kinds of advertisements for lighting fixtures, but nothing related to the 18th century. But we're talking again about what came to be known as the Enlightenment. And one of these people you know very well, the other one you've likely never heard of. And we'll see where we go with this. We'll start with Dr. Franklin. This is sort of an overview, a quick overview of the non-science part of Franklin that you may have learned about at some point in school. If you are curious, there's an excellent biography of Franklin by Walter Isaacson. There is also Franklin's autobiography, and if you've not read that, it's worth reading. I'm going to quote extensively from it in a little bit. But you'll see that he was born early in the 18th century in Boston, a poor family. His father, he was one of many children, and his father actually enrolled him in the Latin school in Boston, a school which still exists to this day. And apparently Franklin covered 3 grades or so in the first year that he was there. And his father became alarmed that he might be thinking about college and pulled him out of the Latin school. So he had not much formal education. He was indentured when he was 12 years old to his brother, who was a printer. Now, basically that meant his father sold him to his brother for 9 years. Franklin learned the printing business and became very successful at it. He was publishing his own newspaper when he was 23, and not long after that began the publishing of the Poor Richard's Almanac, which made him famous across the colonies. You've all seen excerpts from the Poor Richard's Almanac. Along the way, he established the first public library in British America, founded what became the University of Pennsylvania, and was its first president. Was the first postmaster of British America. He was 70 years old when he was elected a delegate to the Second Constitutional Congress. And again, one of the most famous people in the country. He served as the first U.S. postmaster, ambassadors to Sweden and France, and died in 1790. He was arguably, at the time of his death, the most well-known American in the world. 20,000 people attended his funeral in Philadelphia. And that's the side that we learn about in school. At least that's the side I learned about in school. The side that you didn't learn about was the fact that he was also the best known American in Europe because of his scientific endeavors. And I'm going to talk just a little bit about those scientific endeavors. Newton had laid the groundwork for the study of motion, for mechanics. And people like Madame de Châtelet and Voltaire had, actually Madame de Châtelet had extended Newton's work to, in some very important ways, to the notion of energy and momentum and the conservation of those things, which are still two cornerstones of modern physics. People were beginning to look at other aspects of the physical world around them, and today we're concentrating on two of those aspects, Franklin on electricity and the second one on heat. So there was much concern about what electricity was, and at this point the only electricity that was available was what you would call static electricity, the kind of thing that gives you that causes a spark when you reach for the doorknob on a cold winter morning, or get too close to your sweetie and it pops between your nose, and, or whatever. The kind of friction of electricity that you can generate through friction, say by rubbing a balloon on your shirt and seeing what happens to it. And the people who had begun to study it, and it had been known, of course, as a phenomenon for as long as there is recorded history, and probably before there was recorded history, began to develop a theory that said that there were two kinds of electrical fluids, because they began to notice that these materials would attract and repel each other. And the notion that like kinds repelled and opposite kinds attracted was fairly well established, but nobody knew what this electrical fluid was. And that's where Franklin began to experiment. And apparently, according to his autobiography, he was about 40 years old when he began to study electricity. This is the sketch from the inside of his original autobiography. So I guess that's his best judgment of what he looked like at the time this was published. And you know that he invented some stuff. Bifocals. Eyeglasses have been around for a couple hundred years, but Franklin invented bifocals, and these are his bifocals in the collection of the Franklin Institute in Pennsylvania. I'll say more about this in a moment, but this is his first lightning rod, and that invention became very important, and it grew out of his science, and I'll come back to that in a moment. I'll say something more about this Franklin stove that he invented. And you may not know, this is a urinary catheter that he invented, and obviously had some reason for inventing it, but he doesn't talk about that reason in his own words. And this is something that I have heard but never seen before. And this is called an harmonica. It's a glass harmonica that is his invention and became very popular during the 18th century, and especially with people like Bach and Mozart and others composing for the instrument. I've heard it said that it's the most dangerous instrument in the world because these are wine glasses and they are spinning at a pretty high speed, and you're rubbing your finger around them to get the tone. And if it splitters, you don't have much time to move your hand. So anyway, these are some of the things that he's known for. This is what he's best known for. And I'm going to read a little bit about this because there are many aspects of it that I find interesting to consider. So just bear with me for a minute. So you can imagine that on a June afternoon in 1752, the sky began to darken over the city of Philadelphia. The rain began to fall and lightning was in the air, and most everybody was hunkered down inside. But Franklin decided to go fly a kite. He had been waiting for this opportunity for some time. And by the way, he was not the first person to do this. I'll come back to that in a moment too. He had his materials at the ready, and what he was trying to do was to show that the electrical nature of lightning was the same as the electricity that you would experience in ordinary day static light, that it wasn't something different from the ordinary phenomena of electricity as people had experienced it. So according to Joseph Priestley, who is a British scientist who happens to have discovered oxygen, Franklin had originally planned to do this experiment on top of a Philadelphia church spire, not using a kite at all, but using the church spire to draw the electricity. But he changed his mind when he realized he could do the same thing with a kite. So he and his son took the opportunity to walk out into the field to demonstrate the sameness of the electric fluid with the matter of lightning. Dr. Franklin, astonishing as it must have appeared, contrived actually to bring lightning from the heavens by means of an electrical kite, which he raised when the storm of thunder was coming on. The kite was not struck by lightning, as is often portrayed in these books. If it had been, Franklin would not have lived to tell the story. But it did pick up electric charge from the lightning that was in the atmosphere. The kite had a wire on top of it to serve as a lightning rod. And at the bottom of the kite, he had a piece of hemp string, and to that he had a piece of silk string. The hemp, when wet by the rain, would conduct electrical charge. The silk kept dry as it was held by Franklin, and the doorway of his shed wouldn't. So he had a piece of silk string at the bottom of this thing. They flew the kite, he and his son, and waited, and Franklin noticed that the loose threads of the hemp string began to stand erect, indicating they were becoming electrified and repelling each other, just as your hair gets funny when you get a lot of static electricity in it on a dry day. Franklin moved his finger near the key that was attached to a storage device, and the negative charges in the metal piece were attracted to the charges in his hand, and he felt a spark, a pretty hard spark, not a pleasant spark at all. Struck with this promising appearance, he presented his knuckle to the key, and you got a touch from that key and a loud spark, and the electricity from the kite string through the key went into something called a Leyden jar, and I'll show you one of those in a moment, which stored the electricity, and then which he could take and do experiments with as he would with any other kind of electricity. So he was able to do the experiment and demonstrate that the electricity that was collected from the lightning was exactly the same as the electricity he could collect with friction. As I said, he wasn't the first to do that. He was the first to propose it, but two Frenchmen, after hearing his proposal, did the experiment a year or so before he actually did it. And another physicist in the Baltic nations tried it, but was killed when he was struck by lightning. So let's talk a little bit about what Franklin did beyond that. And he talks in his autobiography a bit about this. He could take a piece of, say, a glass rod, and this is something that I know that many students, like Claude and others who have taken freshman physics courses back in a half century ago, did some experiments with. You take a piece of glass rod and rub it with fur, say cat's fur, which is the preferred thing, and it becomes charged. It becomes electrified. And if you take an amber rod and rub it with silk, it becomes electrified. But those two kinds of electricity are different. They're what attract each other. And if you bring them close enough together, you'll get a spark between them. It wasn't very efficient and it wasn't very quantitative, but Franklin finally determined that that instead of what the prevailing theory thought, that there were two kinds of fluids that flowed, one of them behaved one way and one behaved the other, there was really only one fluid that flowed, and that's what we would call electric charge, that was in the charge carried by particles called electrons, although Franklin had no knowledge of that. So he was able to demonstrate pretty convincingly that matter, like this tabletop, is electrically neutral, and that you can do certain things to remove or add electric fluid to it, electric charge. And we still use the term fluid even though there's no fluid involved. It's something else. It's not really flowing in that sense. But when you disturb that by rubbing something onto it or off of it, it becomes electrically deficient or electrically excessive. And that's what causes the charges. It's just one fluid. He coined the terms positive and negative for the two types of charge that were involved, and thought that the positive fluid was the one that was actually flowing, moving between one and the other. And when that positive fluid left, he left behind the negative. He also used the terms plus and minus because algebraically plus and minus offset each other. And he thought that was a convenient way to think about it. So if you have equal amounts of these two things, they offset each other, and you've got zero charge, which is electrically neutral. He did an experiment, if he had had college education at Harvard, as his father feared, he might have been able to realize what the implication of the experiment was. He describes electrifying what he called a silver pint can spelled with two N's, C-A-N-N. The best I can tell, a silver pint can was, in that day, a silver hip flask, a flask that held a pint of liquor. And he electrified it, and it was heavily charged. He could bring something nearby and see it be attracted to the surface. But then he decided to test what was going on inside that can and found that nothing happened, that there didn't appear to be any electric charge on the inside. It was all on the outside of this device. And that was a puzzle to him. If he had had a little bit more math, he could have worked out that the force between those things was what we call an inverse square force, just like the force of gravity, the repulsive force that caused these charges to move as far apart as they could get, which is on the outer surface of the container. But he didn't have that. But still, he did the experiment. Now, instead of publishing these in a journal, he published them in letters to people in France and Germany. And those people took these things into the scientific community in France. Now, let me read you a little piece from his autobiography about that, because there are a couple of things that you might find interesting about it. By the way, his autobiography has lots of chapters, and what he has to say about his science is in the next to last chapter. So you have to read through a lot before you realize that he did anything in science. He talks about how somebody came to visit and gave him some equipment, glass tube and some other things to do experiments with. And he said, obliged as we were to Mr. Collinson for his presence of the tube, etc., I thought he should be informed of our success in using it, and wrote him several letters containing accounts of our experiments. He got them read in the Royal Society, where they were not at first thought worth so much notice as to be printed in their transactions. One paper, which I wrote for Mr. Kinnersley on the sameness of lightning with electricity, the kite experiment, I sent to Dr. Mitchell, an acquaintance of mine and one of the members also of that society, who wrote me word that it had been read but was laughed at by the connoisseurs. So that's what they thought of American science at the time. It was some time before these papers were much taken notice of in England. A copy of them happened to fall into the hands of a philosopher of great reputation in France, who had published a theory of electricity which disagreed with his. He said, rather than write a response to the person who criticized his papers, I concluded to let my papers shift for themselves. What gave my book, the papers, the most sudden celebrity was the success of one of his proposed experiments made by Messrs. Dalibard and de la Torre for drawing lightning from the clouds. This engaged the public attention everywhere. Monsieur Delac, who had an apparatus for experimental philosophy and lectured in front of that branch of science, undertook to repeat what he called the Philadelphia experiments. And after they were performed before the king and court, all the curious of Paris flocked to see them. I will not swell this narrative with an account of that capital experiment, nor of the infinite pleasure I received in the success of a similar one here in Philadelphia. Anyway, he goes on to point out that he was then invited to join the Royal Society of London as a result of the success of the kite experiments and others. One of the things he noticed is that electricity seemed to be drawn to pointed objects. So he could take a piece of glass rod and sharpen it to a point, and either it would attract electricity to that point, or the electricity that was on the rod would drain off at that point. That's what gave him the idea of a lightning rod. The fact that pointed spire was the key thing. That wire that went up from the kite to a point was the key piece in terms of attracting the electricity in the atmosphere. And his invention of the lightning rod was a really major invention, both in this country as well as in Europe. He did not know why that was the case, but modern theory will tell you that the sharper the curvature of the conductor, the greater the tendency of the electric force or electric field around that conductor is going to be. Now, if you think about what I mentioned earlier, how do you pick up static shock when you get up in the morning, you walk across the carpet, and what happens? How do you get shocked? You reach for something metal with your fingers, which are essentially like mini lightning rods. Same thing is true of your nose. Is a place that is easily spark easily leaves or comes to, depending on which way it goes. So Franklin's invention of the lightning rod was really a signal invention in many ways. And I want to say one other thing about his attitude towards those things, because I think it's important. This is also a quote from his autobiography. He says, "In order of time, I should have mentioned before that having in 1742 invented an open stove for the better warming of rooms, and at the same time saving fuel, as the fresh air was admitted, was warmed in entering, I made a present of the model to one of his friends." And he goes on to talk about, he wrote a pamphlet called An Account of the New Invented Pennsylvania Fireplaces and how to build them. He finishes that paragraph that as we enjoy great advantages from the inventions of others, we should be glad of an opportunity to serve others by any invention of ours, and this we should do freely and generously. So Franklin never patented any of his inventions. He always saw them as something that was done for the public good. And he always saw science as something that should lead to practical results. I mean, his investigations of electricity, his invention of the lightning rod, the Franklin stove, all of these things were things that he saw as leading to a practical result that made life better for people. Even the bifocals, the glass harmonica is a pleasure thing. So there's a thread there that I think is an interesting thread. Now let me see what else I want to do here. This is a device called a Leyden jar, Leyden. Basically, it's a glass bottle that has metal wrapped around the inside and the outside of it. And it's a progenitor of a device that you have possibly tens of thousands of on your body right now in the form of the capacitors that are in the chips in your cell phone, if you have your cell phone in your pocket. It is a fundamental piece of modern technology, not in this form, but this is a very important tool because you could store electricity in it. Franklin actually chained together several of these things, these Leyden jars, and built what he called a battery. He called it a battery because I think when he discharged it the spark made so much noise it sounded like a battery of guns firing. It was not a battery in the sense that we have, because once it was discharged, it was done until you put more static electricity into it. But that's Franklin's Leyden jar. Now I put this in. This is newer than Franklin, but again, some of you may have experienced this. It's called a Wimshurst machine, and it's a machine designed to generate static electricity. You've got two glass discs. You can only see one of them there with metal conductors on them and a pulley arrangement so you can turn them. The curious thing is that the two discs turn in opposite directions. And as they turn, charge is induced on them, and it leaks off onto what are called combs that are you can't see because they're horizontal into the thing like little metal brushes. And electricity that is positive is stored on one side, and electricity that is positive, that negative is stored on the other side. These are Leyden jars, just like the one I showed you. And the two balls can be moved relative to each other, and you can get quite a spark with this thing. In fact, I had a student doing work many years ago on one of these that happened to be in the lab at Lynchburg College. Might have been there since 1903, I don't know. But by measuring how far you can get a spark to jump, you can measure what the voltage has to be between those two balls. And she estimated about 75,000 volts for this particular machine. Enough to where when that spark jumps a large distance, you hear it. It's firecracker loud. And you can actually see it. It's again, it's a sense artificial lightning. This is the kind of thing that Franklin was playing with, although not this particular device. Here are some of the terms that Franklin introduced into our language from his research on electricity. And this is a 20-foot tall statue in the Franklin Institute of, and as I said, 20,000 people came to his funeral, most of them not scientists. Well, so that's one American backwoodsman, and his story is really quite amazing. The second one is a little bit different. This gentleman, this statue is on the main street in Munich, Germany. It is one of 4 statues in front of the royal palace of the elector or king of Bavaria, and then much more than that. The other 3 are German philosophers such as Schiller, and this was taken on a very cold day in November several years ago. And you might wonder what it's doing there, because that is an American. Benjamin Thompson was born in this house in the town of Woburn, Massachusetts. In, I can't remember, 1753. Again, it's a working person's house. That house still stands, and there's a Thompson Rumford Museum there. This is sort of a quick study of his life, which I'll run through as I did with Franklin. He was not able to go to school in any formal sense. He was apprenticed as a very young man to a grocer in the town of Woburn. He learned on his own. He wrote a long letter to Benjamin Franklin asking him for information on what makes the wind blow, a whole bunch of scientific things, including the detailed instructions on how to do the kite experiment. I notice he's quite a bit younger than Franklin. He had a very close childhood friend who was older, a man named Lomi Baldwin. Baldwin was also interested in science, and Baldwin actually did the kite experiment and recorded it in his journal. And basically he said that he was getting really nervous when he saw his arms begin to glow out in the field. And so he dropped the kite, and he said the family who was watching him said he looked like he was covered in fire, and they were afraid that he was gone. He became a colonel in the Revolutionary Army. But he was a couple years older than Benjamin Thompson. And apparently they walked the 7 miles from Woburn to Cambridge on occasion to hear John Winthrop lecture on science at Harvard. I mean, there's a tradition that he attended Harvard, but there's no evidence that he ever attended Harvard. But apparently he heard some lectures there. When he was 19, he became a schoolmaster in Concord, Massachusetts. And several months after moving to Concord, he married the wealthiest widow in the county and became a landowner. They had a child, and he began to make himself useful to Governor Wentworth, the British governor of Massachusetts. We don't know exactly how he made himself useful, but we do know that he, at the age of 21, he was, well, actually before 21, in 1773, a year or so before this, he was commissioned as a major in the New Hampshire militia. And there were people who had been in the New Hampshire militia for their whole lives and had never gotten beyond the rank of sergeant. And there was a little bit of animosity about this kid being made a major. And later that year, he was summoned before a committee on safety to explain himself. And that night, he borrowed his brother-in-law's horse and rode away to Boston and never returned. He joined General Gage and chose the other side in this conflict. He moved to London, became British Under Secretary of State for the Northern Department, which meant he was basically the liaison to both the colony, the loyalists who were living in London, and the loyalists who were still in Massachusetts. In 1782, he formed a unit in the British Army called the King's American Dragoons. I'll say a little bit more about that later. 2 years later, he was Sir Benjamin Thompson and a colonel in the Bavarian Army. And he went on to become all these other things in Bavaria and Count Rumford of the Holy Roman Empire toward the end of his career. Now, this is his uniform in Bavaria. This is what got him into to be called before the Committee on Safety. On the left is a letter he sent to one of the British generals in Boston. On the right is that same letter with the secret ink that he had developed. And lots of information on the New Hampshire militia and other places. So apparently he was spying for the British before he got called before the Committee on Safety, and that's why he left home. He invented the secret ink, by the way. Come back to let me just talk about him for a moment before I come back to this. He stayed with the British in Boston until they were forced to evacuate Boston, and he went to London, where he was named this undersecretary. He obviously had some kind of introduction from somebody of import in this side of the ocean for him to walk into London and become Undersecretary of State. he had some leisure in this job, as you might imagine, because there weren't that many loyalists over there. And so he began to do experiments with gunpowder. And those experiments with gunpowder carried over to experiments with that allowed him developing a way to measure the speed, the muzzle velocity of a shell being fired by cannon. And from there, he revised all of the British charts for how you aim cannons, both naval and land cannons, because he had a much more accurate way of predicting how fast the bullet left the barrel, and thus from Newtonian mechanics, which he had never studied in school, he could calculate how far, what the elevation and range had to be. He found himself as master of the King's Royal Armory, again somewhere within a 1 to 2 period time in London. Then there was this affair in London, which some of you could tell me much more about than I know, called the Lamont spy case, in which General Lamont was accused of spying. Well, it appears that Benjamin Thompson was spying for the French while in the employ of the British. So things were getting a little heated in London. That's when he decided that he needed to come back to this country and form this fighting group called the King's Royal, whatever it was that was on the chart, I can't remember, Dragoons. He came ashore in South Carolina and had to recruit 50 people to fight, which he did. There were still loyalists in South Carolina and everywhere else in the colonies in those days. And they had one skirmish with Francis Marion, which didn't amount to much on either side. And then he was deployed to Long Island. He was quartered for the winter in Huntington, Long Island. If you go to the website of Huntington, Long Island, you'll find a lot of mention of Benjamin Thompson, because apparently he quartered his horses in the village church and used tombstones from the local cemetery to build ovens so that his soldiers could bake bread, which they were allowed to sell to the citizens if they wanted to buy bread with the names of a loved one baked into the crust. So he is not a particularly popular person. Anyway, the war ended. He was not involved in any combat in the war. But one of the major driving forces, in addition to getting out of town, was the fact that if he formed this King's Dragoons, he was guaranteed a pension for life. So he went back to England as a lieutenant colonel in the British Army. He applied for a promotion to colonel, and King George says, "I see no reason whatever to do this." 3 days later, he was promoted to colonel. And one can only wonder what caused the king to change his mind. Anyway, he found himself traveling throughout Europe as sort of a soldier of fortune, and ended up in the court of the Elector of Bavaria, the King of Bavaria. And he stayed there for several weeks and eventually went to the king, the Elector, and said, "I have a proposition for you. Your army is terrible. They're expensing the cost of your army, and maintaining that army is killing you as a king. I will take over and I will train them, I will clothe them, I will feed them, and if there's any money left over, I get it." And the king said something to the effect of, "Well, that sounds very good, but I can't have a commoner in charge of my army." So he goes back to London and becomes Sir Benjamin Thompson within a period of a few weeks. Now he's got a title, and he goes back to Bavaria. And he sets about doing what he said he's going to do. The first thing he worked on was clothing. What makes warm clothing? It's cold in that part of Germany in the winter. Well, that was what you might think. But Rumford is a scientist, and he approaches everything in a very scientific manner. This device he called a passage thermometer. And basically, it's a glass tube with a thermometer inside it. That's what the tube going up in the ball is. By the way, he had to build the thermometer and the glass tube because you couldn't go to the store and buy this stuff. So he had to do the glass blowing. And he would take the material he was testing, say he wanted to test silk, and he would wrap it very tightly around that bulb at the bottom of the thermometer. And then he would put the whole tube in boiling water, heat the thermometer and the tube and everything up to the temperature of boiling water, and then he'd plunge it into an ice bath and see how long it took for the thermometer to reach the temperature of the ice bath. And he figured that the more insulating the fiber was, the longer it would take. So he tested everything he could think of: wool, linen, flax, silk, cotton. Basically, they were all the same. And that was very, very puzzling to him, because he was expecting something else. And by the way, his collected papers are in the 2-volume set at the Lynchburg College or University of Lynchburg Library, and he sets all this stuff down very much like you might expect to see in a high school chemistry course, with everything outlined in very great detail. All the numbers are there. You can take his numbers and do the calculations that he did and verify his results, or you could build the thing and do it yourself. But he was really sort of mystified, and I mean, he didn't do this overnight. This takes time, and of course he's got other duties to think about too. Well, eventually he says that he was sitting in his living room or some room in his house, and he noticed that there was a flagon of wine on the windowsill. Now, flagon is a bottle that looks like this, like a chemistry thing. And it was red wine, and it was full up to near the top of the tube. And if you think about it, red wine has precipitates in it. Sometimes you have to decant those off. And he noticed these particles moving up the tube and moving down the outside of the tube. And basically he realized that water was circulating because of the sun warming the bottom of that bottle. And we would call that convection. It's the thing that moves the air. It's one of the major ways in which heat is moved from one point to another. It was really amazing that nobody had thought about that before. Everybody assumed that heat was radiated, as with the sun heating us, or it was conducted. When you put your hand on the hot stove, that heat is conducted directly into your body. This is a new way of transferring heat, and he realized that what makes clothes feel warm is that they trap air against your body and prevent convection from carrying warmed air away from your body. So that gave him some insight into what to do, and he figured out what kind of knit he wanted to make, and he was going to make it out of wool because wool has other characteristics in terms of its drying capacity and other stuff. And so he invented a fabric. But there were no woolen mills in Bavaria. So he went to London, where all the woolen mills were, and nobody would do business with him. You might wonder why. But anyway, so he comes back to Bavaria and says, okay, here's the deal. We've got a real problem in Munich with street beggars. Gangs of street beggars who maim their kids so they look more pitiful, and they were a real social problem. So he says, we're going to round up all these street beggars and put them to work in the woolen mill here that we're going to build here in Munich. And that's exactly what he did. He bought the equipment, outfitted the mill, and rounded up all the street beggars, including their kids, and put them to work. Now, it was not as inhumane as you might think, because he provided quite a bit of food for these people, schooling for the kids, rather than having them maimed and beat on the streets, and salaries, and made the wool for his army uniforms right there in Munich. Now you can imagine that there are a variety of opinions about this within the power structure in Munich, and so he was not the most popular person. This is another experiment he did, and this experiment is a footnote in most physics textbooks. He was thinking about heat, and everybody thought that heat was a fluid called caloric, and that when something cooled, this fluid flowed out of it, and when something was warm, this fluid flowed into it. Well, he was making cannons, and in a cannon, basically you have a drill bit that drills out the hole in this cast bronze or cast iron slug. And he proposed putting the cannon inside a water bath. And as the horses turned the turnstile, the drill turned, bored the cannon, and the cannon got hot. And he put this in Marienplatz, the central square in Munich. It was quite a draw for people to come on their breaks and look at this cauldron of water boiling without any visible form of heat. But the experiment was to weigh the cannon very carefully before he did the experiment, and then at the end to weigh the cannon plus all of the scraps of bronze that were at the bottom, and see if you could measure the weight of the fluid that had left. And what he found was that the cannon didn't, and the scraps were the same weight as the cannon in the beginning, that nothing left the cannon. So he concluded that heat was a form of motion, which we understand it to be. And that was the first and seminal experiment that indicated that there was a relationship between mechanical energy and heat energy. And of course, there was a great deal of interest in the heat energy in the 18th century because people were trying to understand how to make steam engines work better. Watt had patented his engine, Newcomen. So there's a lot of interest in that. This is another picture of the cannon boring process. This is another Rumford invention, again based on science. It's hard to see in this drawing. But basically, he redesigned the fireplace. Old fireplaces had flow that was turbulent and did not flow up the chimney, and you got a room full of smoke. And that was a huge problem in London and other cities across Europe in the 18th century. He redesigned a fireplace where there was a different kind of flow. It made laminar flow or smooth flow and did not kick smoke back out in the room. And if you have a brick fireplace that does not smoke up your room, you've got a Rumford design even today. You go down to the hardware store, and one of the choices you have are Rumford fireplaces, metal or otherwise. This endeared him greatly to the citizens of London and other places. Amazing invention. This is a caricature of him standing in front of one of his fireplaces. This is a pamphlet that he wrote. And you can read this. Let's give you a little wider one. This is a part of it. Can you read that? Again, these F's are not F's, they're S's. Its taste is very agreeable and its flavor uncommonly so, but its principal excellence depends on its salubrity and on its exhilarating quality. It excites cheerfulness without intoxication and the pleasing flow of spirits, which at occasions lasts many hours and is never followed by sadness, languor, or debility. It diffuses over the whole frame a glow of health and a sense of ease and well-being, which is exceedingly delightful. Now, this is part of a pamphlet, but it's also part of another invention that he made. This is a drip coffee pot. That's his original drawing for it. He invented a new kind of lamp, one that actually gave out light, and a way of measuring how much light came out of it in terms of something called a standard candle. You may have heard the term foot candles somewhere along the way. That goes back to Rumford and his work in that. On the right are models of his field coffee pot, which worked just fine. This is a picture of him later in life in front of an industrial-sized stove and furnace for heating a whole house back there that he had designed. He was a very curious person. At one point, he was in London celebrating the success of his fireplaces, and he was called back to Munich because Munich was in danger of being invaded. The French and the Austrians were fighting, and the French army was camped on one side of Munich and the Austrian army was camped on the other. So Rumford goes back to Munich and somehow convinces the French not to invade. He says, if you want to invade, I'll make sure the Austrians don't. We don't want to see our city messed up. Did the same with the Austrians, and within 3 weeks, both armies had left. And once again, he was regarded as a savior of the city without having to fight anywhere. But apparently, he had a personality that was pretty persuasive. One of the things he did for the people, in addition to getting the streets cleaned up of street beggars, was to convince the king to turn over his hunting grounds to create a public park. That public park is, if you've ever visited Munich, you've probably visited the English Gardens. And that exists as a public park because of Benjamin Thompson. Anyway, after the affair with the French and Austrians, the king named him a count in the Holy Roman Empire, and he chose the name Rumford, which was the previous name of the city of Concord in Massachusetts. This is Rumford House. This was built for him, for his residence along the English Garden. Again, photographed on a very cold November day. And that's again the same statue. We spent several months in Germany, and that's the only American statue I found anywhere that I visited. He gave $5,000 each to the American Academy of Sciences and the Royal Society of London to endow a prize called the Rumford Prize, and it consists of this medal and a cash prize. Now, $5,000 given in 1760 or so is worth substantially more than that today, and that prize is in the six-figure range if you win it. So he endowed that. He created something called the Royal Institution of London to benefit the people of London and Europe, primarily to make the things that he had invented available to anybody who wanted to make them. No patents. Again, very much like Franklin in that respect. The Royal Institution still exists, and I'll say more about that next time, because he not only endowed it, he bought the property that housed it. he hired the first director, and when that person left, he hired the second director, a man named Humphrey Davy, a well-known British scientist. And Humphrey Davy hired as his assistant a young man named Michael Faraday, whom we'll talk about next time. And that's his silhouette on the Rumford baking powder. So you might wonder why you've never heard of this guy. Not only was he important in science, he was important as an inventor, had an incredible career, but he was not the kind of person that people felt endeared to because who knows how many people he was spying for and other aspects of life. He could be very charming. Late in his life, he married the widow of the great French chemist Lavoisier, who was apparently a very lovely lady. But he could also be spiteful. When people complained to his boss in Germany, in Bavaria, about his arrogance, he found ways to repay them, including having the king force them to bow in front of him and ask for forgiveness. So he was not a nice person, but he was an incredibly brilliant person. And with that, I'll stop and see what kinds of questions you might have, if you have any, or comments.